Now I'm trapped.
That's kind of scary.
Right? No pressure.
Oh, he moved it.
It's bigger than the normal stage.
Okay, so today we'll be hearing from Leilani. She's a graduating PhD student from MIT, and she will be telling us about her database systems for scalable visualizations. Thank you, Jenny.
Physical and biological sciences are becoming more data-driven over time due to overwhelming amounts of data being collected from satellites, field sensors, devices, medical devices, and more. And in order to analyze this data efficiently, scientists need ways of visualizing it efficiently. Where when I say visualization, I mean an interpretable image created from an oftentimes non-visual data set. And scientists use visualizations to extract patterns, identify anomalies, and debug their analysis workflows. And more. Of course, scientists could use existing visualization systems to do this analysis. Some systems you may have heard of include Tableau, Power BI, and Plotly. But these systems focus on commercial analytics, where you're generally not visualizing very large amounts of data. They're not doing deep domain-specific analyses, so you don't require deep domain-specific knowledge to perform the analysis. And you are visualizing the data directly, so you're not performing any complex analyses directly on the data before rendering it. For example, in the main use case for commercial analytics, in producing performance reports, such as analyzing total sales over time or the popularity of products in certain regions. In contrast, scientists need more flexibility when creating their visualizations. Specifically, they need to be able to do those complex analyses before actually rendering the data, oftentimes in the form of a database query. So let's consider a use case with satellite sensor data collected from the NASA MODIS, or the Moderate Resolution Spectroradiometer. Basically, a satellite instrument aboard two of NASA's satellites, which collects a lot of light measurements across many different wavelengths, 36 to be exact. And using this raw data, you can track vegetation, hurricanes, phytoplankton populations in the oceans, and snowmelts over time, or snow cover. But the situation here is that in all of these use cases, you cannot render them directly from the raw data. You need to apply some sort of data transformation, such as a snow cover function or applying a vegetation function in the form of oftentimes in the form of a database query, before you actually render the results as visualizations. And then the MODIS data itself can be pretty challenging to work with. So it has multiple dimensions, latitude, longitude, and time, some of which may need to be pre-processed before analysis. And as I said, it has many different measurements that it takes. So these columns represent each of the wavelength of light that it measures. And I'll just point out two, B6 and B4, which are useful for snow cover, which are shortwave infrared and visible green light. And it also has additional metadata that it collects, so that when you look at a particular measurement, you understand the context for where and when that measurement was taken. So what we really need are systems that allow you to visualize analyses or database queries rather than the raw data itself. So for example, in the case of snow cover, we want the ability to execute the specific snow cover query that we want to visualize. And then we want the system to return, rather than raw results, an interactive visualization where we can pan and zoom through our snow cover results to see them in more or less detail. And here, our snow cover visualization has dark blue pixels representing areas that are likely to have snow cover, and then gray pixels where areas are unlikely to have snow cover. And furthermore, with these data sets, we find that they generally don't fit on an individual person's laptop. And you really need one or more servers to efficiently manage and process the data. And these servers are oftentimes a shared resource that other applications and other users are working with as well. So you can't assume that resources are plenty and bountiful. So we need to do this efficiently.
Just quick.
Yes.
Does the analysis fit on a laptop? Now I know the raw data doesn't, because what about the thing that produces that map?
The visualization does fit on a laptop. So I'll talk about this more later, but it does fit on a laptop. So what's powerful about this setup is that now, instead of focusing on the raw data and focusing on queries, the user can perform a more iterative analysis where they can get more targeted results or better results by updating or writing new queries. And then if we can visualize them quickly, we can allow the user to visualize each of these steps quickly and then perform a longer form analysis in a reasonable amount of time. And then here, the user has updated our snow cover query by adding a filter for areas with high likelihood of snow, where NDSI is a representation of that. We want these systems to also be general purpose. We don't want it to be just for satellite sensor data or whatever particular sensor that we're using. For example, we should also be able to look at EKG or heart rate monitoring data with the same system. In this case, we have a query where we're selecting all the data for a particular patient, which corresponds to a specific waveform ID. And the system should give us an interactive accurate visualization of those results. But we can pan and zoom through this data to see it in more or less detail.
Waveform equals is like the patient ID somehow? Is that what you said?
Yeah, so the waveform ID corresponds to a particular patient. You can even think of it as a specific period of time for that patient. But here you can just think of it as one patient. And ultimately, my goal is to build easy-to-use, data-intensive systems for complex analytics, and particularly in the context of visualization. And in pursuit of this goal, I've investigated various aspects of database optimization and usability, involving projects such as extracting thousands of visualizations from the web, which we can use to make better sense of how people create visualizations in the first place, creating interactive visualization interfaces that allow people to make sense of the queries that they're writing over complex data sets, low-level optimization techniques such as analyzing and improving the performance of database join operations on highly skewed data sets, a common case for data analytics. But in this talk and in my thesis, I focus on building systems that enable large-scale data exploration by minimizing system latency. And I call these systems exploratory browsing systems. For the rest of the talk, I'll provide a context for exploratory browsing. So what does that mean? I'll talk about the particular system I've been building throughout my thesis called Scalable to support exploratory browsing. And then I'll discuss my future directions of research in data analytics. So in exploratory browsing, the user is interacting with a visualization interface on a client machine, such as the user's laptop. And this client machine is connected directly to a database management system, or DBMS, running on a remote server or a group of servers. And examples of DBMSs you may have heard of include Postgres and MySQL, and more complex systems like Vertica and CyDB. In my thesis work, I use CyDB as the data processing backend. And here we are visualizing snow cover again, where areas that are likely to contain snow have red pixels, and areas unlikely to contain snow have green to blue pixels. And we created this visualization using a query, like I showed you before, a snow cover query. So now when the user interacts with the interface on the client, a query is triggered from the client to the DBMS. Then the DBMS executes this query and returns the results, and the client uses them to update the user's current visualization.
Is there a lot of snow in the Philippines?
That's a great question. So in this particular visualization, we did not do a great job of filtering around the coastlines. And it turns out water looks a lot like snow using this calculation if you don't filter it out. So unfortunately,
You need another query. That's a problem.
Okay.
It's gotten better since then, but good question.
Maybe it's the beach.
I like the beach. Okay, sorry. Yes.
Yes. So the challenge here is that DBMSs are not necessarily designed to return results at interactive speeds. But obviously, data exploration systems rely on interactivity so that the user can explore the data quickly. So in this context, when the client is sending a query to the database, it may take a long time to return results. And this is problematic because it will insert lag into the system and disrupt the person's analysis process. However, even though there may be a significant amount of data that may need to be processed in the DBMS, these interactions that are triggering the queries in the first place are tied to specific interactions with the interface. And then these interactions correspond to specific data regions. Furthermore, The actual interactions that the user is performing are not random. For example, we found that when users pan, they tend to pan multiple times in a row in the same direction before changing direction or changing interactions. And then also similarly, when users zoom in, they tend to zoom in multiple times in a specific region before changing their interactions or changing direction as well. And then using this context, we can develop behavior-driven optimizations, where the idea is that we can predict ahead of time the user's behavior. We can provision in the system for the specific interactions corresponding to that behavior to improve performance. For example, we can aggressively filter the underlying data, so we're only executing queries on the regions the user can actually touch and is likely to touch in the future. We can compute supporting data structures ahead of time before the user starts exploring, so offline, if we have an understanding of how they're going to explore that data in the first place. And what's great about behavior-driven optimizations is that they're DBMS and hardware agnostic, so we can apply them in a variety of contexts. And in exploratory browsing, we focus on two target metrics, responsiveness and efficiency, which you can think of as online performance versus offline performance. And I mention this because we're not focusing on visualizing raw data, where you get the data, you visualize it, and you're done. We're looking at a longer form iterative analysis, where you may have to create visualizations multiple times for each query the user wants to explore. So with responsiveness, we say that the system should provide visual feedback to the user within 500 milliseconds of their interaction. And we chose 500 milliseconds because past studies have shown that users get noticeably worse at exploring their data with system latency beyond 500 milliseconds. For example, they might get distracted, they might get frustrated. One study found that if they made the delay too long, people just basically gave up. And then with responsiveness, we have to balance our goal to have interactivity with considering that they are also doing a longer form analysis. So every time the user issues a query, we have to visualize it. And one way of ensuring that after the visualization's been created, the user has fluid interactions is to build a large number of supporting data structures offline ahead of time. This works great when the user is visualizing exactly one query, but it can be very time consuming overall if they're not. So with efficiency.
Why do you visualize every single query that they would make? If I scroll a little bit, and then you're going to start computing that, and then I'll scroll a little bit more. Now maybe that you don't need all the results of the first one because I've scrolled it away.
Well, the problem is, if the query the user asks you to compute takes a long time to execute in the first place, then you do not necessarily want to wait until the user scrolls to execute that query, because that will introduce lag into the system. So one way to completely avoid, to basically mitigate any risk of executing any slow queries, you can just pre-compute everything in advance the user might possibly do as an interaction, which existing systems actually do. But in my work, which I'll talk about later, we consider exactly what you said. If the user is not even necessarily going to move to particular regions, why should we bother doing that?
Anything better to do?
Sorry?
Have you got anything better to do?
That's a great point. But when you're working on limited time, limited resources, you definitely don't want to waste them computing stuff the user's not even going to see. And that's the point of the efficiency metric.
Quick question.
Yes.
How long does it take to compute, let's say if I move a frame, they compute that frame's example. So you give me 500 milliseconds as the boundary
Yes.
for interactivity. How long does it take to actually do the computation? How much ahead do I have to predict?
That's a good question. So it depends on,
I figured so.
it depends on the query, and it depends on the size of the data set. It also depends on other things, like there are different resolution levels that we support, so it also depends at what resolution level the user is looking at, because that will dictate how much of the data set needs to be processed as part of that query. So in what we've been looking at, it could take, in terms of data retrieval, it could take from a second to a couple seconds. In terms of data processing, it could take minutes. It could also be even longer than that, depending on the structure, the underlying structure of the system on the back end. Yes?
What is the kind of query that usually, users ask for? Is it some kind of a simple aggregation that happens? That people ask for, or is it some more complicated function of the data?
So just if all you're doing is aggregation, many existing systems already support that. That's a very simple, that's very basic functionality. What I'm looking at is people wanting to apply functions or do other things like database joins prior to visualizing the data, which is more complicated.
You mentioned 500 milliseconds, but you also mentioned earlier that the visualization processing software runs on the user's laptop.
Yes.
So the 500 milliseconds include both the retrieval time from the server plus the processing
That's a
local,
good question.
or?
So no, it only includes data retrieval, but that's because in measuring the amount of time it takes to render the resulting data, the data that needs to be rendered is much smaller. So it goes much faster. Looking at current exploratory processing systems, you can partition the space in half based on the output format, basically how you want the results to look before you visualize them, such as individual tuples with sampling.
I'm sorry. So does that mean you're doing some of the complex computations on the server before?
Yes.
And all that's coming back is basically some information.
Yes, the data is ready for rendering once it's on the client. All of the heavy lifting is done by the database management system on the server. Great. So you can partition this space in half based on output format, sampling, and aggregation. And then on top of that, you can further partition the space into 3 groups based on optimization techniques applied to support interactivity. And each of these groups is separated based on when they're utilized in the analysis process. So with pre-computed structures, you're building, say, zoom levels or other kinds of data structures offline before the user starts exploring. There's also predictive techniques where you're trying to predict where the user is going to go and then provision accordingly. Those are done just before the user's interactions, which are also queries. So just before the user's interaction queries. And then last, you have progressive or iterative analysis, where you're showing them more tuples over time or showing them more of the aggregation results over time. And this is done after the user's interaction because you're showing them a progressive result. What's unique about Sculpin is that it actually spans all 3 of these optimization techniques in comparison to existing work, which usually applies pretty much just one. So that I've given you context for exploratory browsing, I'll move on to talking about my exploratory browsing system, Sculpin. So Sculpin supports detail on demand or pan-zoom browsing of multidimensional array data. And the goal of Sculpin is to balance not only visualizing queries quickly, but also conserving resources during this offline pre-computation process. Because again, the servers that are being used on the back end are a shared resource, and resources are not bountiful and plentiful for Sculpin. It could be running directly competing with other applications and other users that are trying to use resources on these systems. So to support this goal, we have a server-side middleware layer that's inserted between the client and the DBMS, which is in charge of actually running our behavior-driven optimizations. And in Sculpin, we make 5 major contributions. An analysis model to describe how users explore multidimensional array data, 3 behavior-driven optimization techniques, predictive data-prefetching, incremental data processing, and visualization network caching. And then to evaluate Sculpin, 2 user studies with scientists exploring real-world data. And we also collaborated directly with scientists to develop these studies. So Sculpin supports multidimensional exploration using what's commonly known as a coordinated view visualization design. This is not novel. It's a standard technique in visualization literature, where in Sculpin, to explore, say, a 2-dimensional data set like snow cover here, where again, likely areas with snow are blue and unlikely areas are gray. You have an X and a Y axis, longitude and latitude, and the user can simply drag along these dimensions to explore the data in more detail. To support more dimensions, say 3 dimensions with snow cover, so latitude, longitude, and time, we can add a time series visualization to the interface. And Sculpin is not limited to 2 or 3D exploration. It can support exploration along more dimensions by adding more visualizations to the interface. So here's an example of a user exploring in Sculpin with snow cover data. They have 2 views, a latitude, longitude view, and a time view. And here they're using the latitude, longitude view to explore the Sierra Nevada mountains in California. And then here's the same user manipulating the time view to see changes in snow cover per day for the US. So to support efficient data processing and retrieval, we implemented a tile-based data model in Sculpin, where we...
I'm sorry,
yes.
can you build animations that way? I mean, you have to actually drag it like that, or do you say, visualize this over the 24 hours?
That's a great question. So that's really a matter of the design of the interface. So most of my techniques are focused on the back end of the system, but it would be great to develop more flexible interfaces in the future. And specifically in our user studies, we did find that users were asking for other different kinds of interactions, say buttons, maybe for days instead of dragging, or in videos to see change over time without having to click through.
But as you change the user interface, that can change your predictive model, what data they're going to go to.
Yes,
For instance,
it
if you
could.
start sorting by places with low snowfall, I click around them. I'm not local anymore. I'm jumping around the
That is
world.
a fantastic point. So we started with a basic interface that's commonly used, and we found that we provide significant performance improvements in that context when you consider the user's behavior. And for my future work, I would love to move to supporting a richer set of interactions. But I'll get to that at the end of the talk. So let me first talk about the data model. So what we do is we create multiple resolution levels of the user's query results, or zoom levels, and then we partition these zoom levels into what I call data tiles. So first, how do we create these zoom levels? We take the user's query results, or the user's query, say represented by this grid, since we're working with array data, and we do windowed aggregation, where we aggregate every n cells of the array, and n represents our aggregation window. We use a larger n to create coarser grained zoom levels, and a smaller n to create finer grained zoom levels. Then we take each of our zoom levels, and as I said, partition them into fixed width blocks or data tiles, which you can think of as the general purpose equivalent of image tiles and other interfaces, like Google Maps. So with the Sculpin architecture, we have a visualization component running on the client, which manages the multiple visualizations that I showed you in the Sculpin interface. And then we have our middleware layer, which is in charge of our optimizations. And the first component of it is our prediction framework, which is responsible for anticipating the user's future interactions and prefetching data tiles. We have our tile builder component, which is responsible for executing the queries to actually compute the tiles and store them inside EP, and also to retrieve tiles so they can be cached. And then in Sculpin, we have 3 different caches for which we use to manage tiles. 2 main memory caches on the client and in our optimization layer, and then a disk-based cache to store computed tiles inside EP. So then I've talked a little bit about the system design. I'll go into our specific optimizations, but first I'll talk about our analysis model and our prediction framework. So before Sculpin can actually make any predictions, it has to have some sense of what it means to monitor and predict the user's behavior. And to capture that, we developed this 3-phase analysis model where we say users explore data in 3 different phases: foraging, sense making, and navigation. And to explain what each of these phases are responsible for, I'll demonstrate with an example. So say we're exploring snow cover data. We're here, snow is red pixels, areas that are unlikely to contain snow are green to blue pixels. And we're looking at the US and Canada. So here we're interested in clusters of red pixels, which represent lots of snow, which in this case represent mountain ranges. So we start out in the foraging phase, where we're at a coarse grained zoom level, looking for a region of interest to explore, such as this mountain range at the top of the visualization. Then we switch to the navigation phase, where we're zooming in towards that region. And then once we reach an appropriate zoom level where we want to explore, we switch to the sense-making phase, where we're at a finer grained zoom level, exploring this mountain region. And these boxes represent the tiles that we request along the way. Then once we've thoroughly investigated this area, we return to the navigation phase where we're zooming out so that we can go back to a coarse grained zoom level in the foraging phase to identify a new region of interest to explore, such as this cluster of red pixels in the bottom right-hand corner. So using this 3-phase analysis model, we first developed what I call a 2D predictor, where given a 2-dimensional visualization, like the snow cover visualization I just showed you, we can make accurate predictions about what interactions the user will perform in the future, and then prefetch the corresponding data tiles. So to do that, we developed a phase predictor and model manager, where the phase predictor, given information about the user's recent interactions, such as a panning interaction, will make a prediction about what analysis phase the user is currently in. In this case, suppose the user is in the sense-making phase. Given this information, we have a model manager, which actually is in charge of predicting data tiles. And to do this, it runs multiple low-level prediction algorithms, or what I call recommendation models in parallel. In this case, models 1 and 2. So given this, and the way it can more efficiently perform its prediction is by allocating space to these individual recommendation models. So in this case, the user's in the sense-making phase. Suppose model 2 is better than model 1 at making predictions during this phase. Then the model manager will allocate more space in tiles to model 2 than model 1. In this case, 4 tiles versus 2 tiles. Then these models are run in parallel to actually make the predictions. And in this case, model 1 predicts that tiles A and B will be requested by the user, and model 2 predicts that tiles C, D, E, and F will be requested. So in the 2D case, then these predictions are consolidated and sent to our tile builder component for retrieval. And I'd like to reiterate that here you see 2 recommendation models. And specifically for Scalable, we focused on developing 2 models, our action-based and signature-based recommendation models. But Scalable's not limited to 2 models. It's designed such that you can add as many models as you want to support different data sets and different forms of exploration. Yes?
How did you? So the model is a model of the behavior that a person's going to do because we know that they're sensitive.
Yes.
And so you give people the tools to build those models, or are those models built into the system, or?
So we've developed 2 models that are built into the system. We make it easy to add models, but we do not necessarily give people tools to create the models in the first place. That's a good question. That would be great future work.
So the models in this case are going to be things. I mean, if I look at the mountain range example, the model would be something like I'm looking at an area of high density.
I'll get into that. I'll get into that immediately after this slide. Yes.
How did you go about coming up with a set of interactions? So I'm guessing they're partly time dependent, that like a pan, could be short, could be long, and that it probably really affects the prediction accuracy.
That is a good point. So currently we focus mainly on direction. So what direction is the user panning? It would be we have built-in infrastructure to record other aspects of the interaction, such as the time, also the drag distance. If someone's doing a big drag, they might be wanting to move through tiles very quickly. But that will be basically immediate future work to incorporate those other metrics. Yes.
Google Maps seems to do something like this when it's showing me traffic.
Yes.
Information. Do you know if they're doing similar things to what you're underneath to make their predictions?
So I think they're careful about making a lot of information about what they do public, but I'm pretty sure they're doing similar techniques specifically for like satellite images. But this is more for general purpose data exploration where you're executing queries on the database. So it's not just for traffic data. For example, like you can use it for EKG data, like I mentioned earlier. We've looked into using it for brainwave data. We've also looked into using it for astronomy data. So it's not limited to geospatial maps. All right, so I'm gonna move on back to this slide. So, like I mentioned, we have 2 types of recommendation models. The first is action-based recommendation, where the idea is that the user consistently moves in predictable directions. And we apply this using Markov models. So just to give you an example, say we're exploring snow cover like before, and the user pans right and down and right and down. Intuitively, we see this as a pattern of the user panning diagonally to follow a mountain range along the Pacific coast. Though you may not be able to capture all of that information with a Markov model, you can capture at least the directional pattern and extend it to make predictions. For example, that the user will continue to pan right and then down.
Well, last one seems wrong.
Sorry, what does that seem wrong?
Because the mountain range is turned. Right. I was wondering which way you're going to go, because if I just looked at the pans, I would predict that.
Yes.
If I look at the mountain range, I'd go different
So
direction.
we're looking just at the patterns of the user's interactions for this model. But you're absolutely right. The fact that the user is seeing a mountain range is influencing her interactions. And
that's actually data you have, too.
I will get into that very shortly. Very astute audience here. So we have our signature-based recommendation model, where instead of fixating on the particular interactions that a user is going to perform, we instead look at the tiles that have been requested as a result of those interactions, and then assume that the user wants to see more of the same thing. And to do this, we track the user's current location, and then identify the neighboring tiles surrounding that location, and then rank them by visual similarity. And we use various metrics to compute similarity, such as calculating a histogram across all of the tiles for a particular data attribute, and then comparing those histograms for similarity. So now in this case, let's revisit this example, where instead of panning right and then down, the user pans down 3 times in a row. These boxes represent the user's current location in the center and the neighboring tiles surrounding it. What the action-based recommender would have done, so similar to what you asked, is it would assume that we're going to continue this pattern and pan straight into the Pacific Ocean. Of course, this is a bad prediction because we know there's no snow there. So that's dumb. Let's not do that. Instead, the signature-based recommendation model would see the basically high amounts of snow and the tiles that the user's been visiting recently, identify these tiles as being visually similar, and then predict that instead the user might pan right or up back the way they can. Yeah.
So you want to do this though without computing everything in those tiles. I mean, I'm not sure I understand this exactly, but if you you don't want to compute all the information in those tiles, you want to wait until you decided you want to compute the information in those tiles.
That's a great question.
So I assume there's some kind of sampling here.
So we developed this prediction framework in 2 phases. The first phase, we assume that we know everything. And the second phase, we don't assume that. But that is a good point because we don't, that's part of this research has not yet been fully investigated, and I would love to look at that in the future.
So, and just in terms of that
Yes.
model with the similarity, so you mentioned there could be lots of, so is it that you calculate, you have predefined ways of defining similarity between tiles?
Yes.
Data.
We have
And then
several
you look to
metrics
see
that we
which ones of those seem to correlate with the patterns of motion, and then pick that model of similarity to be the predictor.
So in our signature-based recommendation model, we don't consider motion at all. We only use the user's current location and then identify basically a neighborhood and then rank their visual similarity. You could do something more sophisticated where you physically combine these 2 algorithms together. But right now, we treat them as black boxes and allocate space to them based on how well they work. Yes.
For the action-based recommender or predictor, if you use just the individual users' interactions, or do you use the collective of all users?
That's a great question. So we train the models on all users.
Okay, so it's one model across all the users.
Yes, but that's a fantastic question because what would be really cool is if we could basically create behavioral profiles. And there has been some existing work on that, but it'd be fantastic to develop that further. But right now we train on it.
So you can take advantage of the fact that the user A did not hand down either.
Yes.
User B will not get a misprediction.
Yes, that would be one nifty trick specifically for the action-based model. Assuming that users always do rational behavior that makes absolute sense no matter where you are in the data set. Of course, that might be a tall order, but you know. I'm sorry, you had a question?
I said I'd rather hear you talk.
I like my talk too. So this prediction framework works very well, but it was specifically for the context of 2D exploration, where we have a single visualization, such as the snow cover visualization on the right. But Sculpin is designed to support multidimensional exploration. So how do we take this 2D predictor and extend it to a multi-predictional framework? And then here we have the predictor, the diagram of the predictor on the left. So looking at it as purely a data prediction problem, you would quickly see that we run into, and then here we have the action-based and signature-based recommenders now instead of model 1 and model 2 like we saw before. But what's interesting here is that when you look at it from a pure prediction perspective, pure data prediction, we have a dimensionality problem. Because the more dimensions we add to the data set, the more data tiles we have. Specifically, you have an exponentially increasing number of tiles with increasing numbers of dimensions. So from this perspective, you would just throw up your hands, maybe throw your chalk on the floor, just give up. This seems intractable. How are we going to make predictions here? Well, actually, what's very cool about this research is that we're not just considering databases. We're not just considering the data processing perspective. We're also considering the user interface perspective. And that's where it really helps us here. Because in the Sculpin interface and other interfaces like Sculpin, you have multiple visualizations that the user is utilizing to actually perform their exploration. And each visualization is connected to 1 or 2 data dimensions. And we know that the user will explore with one visualization at a time. So rather than worrying about trying to predict which dimension and what tiles are going to be prefetched without considering the interface, we focus first on the interface. Because we already have a predictor that works well for one visualization. So what we can do is make copies of it to predict for all of our visualizations. So the last hiccup here, though, is that since we know the user is exploring with one visualization at a time, if we allocate equal amounts of prediction space to every one of our predictors, we're really losing out on resource utilization here, because we know that only one of them will actually be right. So to take that into account, we have a visualization we have a visualization selector, where its job is, given information about the user's recent interactions, say the user just performed a pan in visualization 2, the vis selector makes a prediction about which visualization will actually be utilized in the future. In this case, it's probably going to be visualization 2 again. So given that information, it allocates space to the predictors, where here, the predictor for visualization 2 is given more resources than predictor 1, and then runs the predictors in parallel to prefetch tiles in anticipation of the user's next interaction. So I just talked about basically the most sophisticated and most interesting component of Sculpin's 3 behavior-driven optimizations, but it has more. And I'll talk about our other 2 optimizations, which are incremental data processing and then visualization and caching. Yes?
Before we move on to this, your example of a mountain in a 2D visualization shows limitations in one dimension to another, particularly for high-dimensional problems. This is a big problem everywhere. You're saying, let's choose 2 dimensions out of what could be a high-dimensional tiled, uniformly sampled data set, and let the user decide how to switch with these orthogonal planes in a high D space. But very, very often, the interesting data is diagonal in the higher dimensional space. How are you going to find that?
That's a great question. So what I think is it's going to depend a lot on, so I think what we need to do is we need to study more how people interact with high-dimensional data sets in this context.
But there are a lot of high-dimensional tools already available. The transforms that will fit ellipsoids to find those diagonals. There are lots and lots of data analysis tools that are not restricted to a fixed set of coordinate axes.
That's a great question. So that's a good point. Yeah. What you can do is you can take higher dimensional visualizations and use them in the interface instead. But what I meant is that even though many of these tools are available, I don't think there's a lot of behavioral data on how people make these decisions.
Okay.
And I think it would be great to investigate that further before we make assumptions about how they're going to, what their behavior is going to look like ahead of time.
Okay, so let's say we have this high-dimensional analysis. People do principal component analysis on it, and they say, here are these diagonals. What will your system be able to do for them? How can they know those diagonals are there? What can they do in your system to see?
Okay, so this is a good point. There are certainly limitations to the system as is in terms of those visualizations. So if the most interesting stuff is along diagonals across multiple dimensions, Sculpin's interface basically restricts what you can do there. And it would be important work to see for high dimensional data sets. So let me reiterate that even at low dimensional contexts, there's still a lot of performance drawbacks right now with existing systems. And my work aims to address that. Okay. And it would be fantastic to move to higher dimensional spaces, but I think there will need to be basically laying of some groundwork to move in that direction.
Okay, so is it fair to say that it's been designed mainly with geographical data systems and low dimensional gridded 2D or 3D systems? It's best.
So I would say lower dimensional. I would say lower dimensional, where you're not necessarily looking particularly at the diagonals, where there's still interesting stuff to see among pairings of dimensions and individual dimensions.
Okay.
Because even in a higher dimensional context, it's still the case that you can certainly see interesting things with this
but
setup.
Smaller dimensions, 2, 3, and 4. Not hundreds of dimensions, as you find.
Certainly not hundreds of dimensions. Okay. But I would push back on the assumption it was only for 2 and 3D.
How do people visualize those at all?
I think I'd like to move on with the topic. Sure. Thank you. We can talk about this more later. Okay. So with incremental tile building, which is the second behavior-driven optimization in Sculpin, we really want to focus on only building the tiles we need. What that means is, if the user's not going to look at it, we definitely shouldn't be computing it. But we do run the risk that if we don't compute it and the user actually did want it, we could take a penalty in latency as far as having to compute that tile after it's been requested. So to take this into account, we have basically a 2-pronged strategy where we have offline tile building and online tile building. With offline tile building, we aim to compute the tiles corresponding to the most expensive zoom levels first, because they take the most time to process. And then we have an offline process that basically tries to build tiles just in time ahead of the user as they explore. So since we've already built the most expensive tiles, this more exploratory pre-computation is less expensive. So with the offline tile building case, say here that we have a data set where we have 4 zoom levels 0 through 3, that we might end up computing. And the size of the tiles here represent how expensive it is to compute those tiles, where zoom level 0 is definitely the most expensive. The first step in the offline tile building process is that we calculate a build estimate, or basically the average amount of time it takes to build tiles at this particular zoom level. Suppose that here at zoom level 0, it takes 50 seconds to build a tile, and then at zoom level 3, it takes 1 second.
Given the open-endedness of your system, how do you know that? How do you get those estimates?
We basically measure it empirically by sampling from the zoom levels, which is pretty cheap compared to building every single time. So then, given these build estimates and a predefined build threshold, which here is set by default to 1 second, the tile builder component, which is in charge of all queries for tile building and fetching, will compare the build estimate to this build threshold, and then build all the tiles for the zoom levels that have a build estimate greater than the threshold, so greater than 1 second. So in this case, zoom levels 0, 1, and 2, those tiles will be computed ahead of time. With the online tile building process, we basically predict ahead of time when the user is going to move to regions where the tiles have not yet been built, and then build them just ahead of the user. And to do this, we just reuse our prediction framework. So the last optimization technique in Sculpin is visualization and word caching, where we have 2 sets of techniques: cache replacement policies to manage tiles in an individual cache, and then cache coordination protocols to manage tiles across all of our caches. So with the cache replacement strategies, we have 2, navigation and ranking based. So with navigation based, suppose these tiles represent the current state of one of our caches. These 4 represent the user's current location, and these arrows represent how far the user will move in any particular direction after a single interaction. The way the navigation-based or cache replacement policy works is it evicts any tiles that are beyond 1 interaction, that are more than 1 interaction away from the user. So in this case, the 6 tiles on the right will be evicted.
Is it fair to say a tile is a screen full in this display, or is it more abstract than that?
So that is an adjustable parameter in Sculpin. You can make the entire screen 1 tile. You can make it multiple tiles. So for example, I think Google Maps has multiple image tiles on the screen.
Okay, but it's generally related to the display of the data.
Yes.
Okay.
And it's configurable, so it's not one-click. So we also have our ranking-based cache replacement policy, where suppose this is the current state of one of our caches. We have tiles A, B, C, and D stored. We send a list of these tiles to the prediction framework. Then it returns a filtered and ranked version where the tiles on this list are likely to be requested to the user in order of likelihood. The ranking-based policy will evict any tiles that are not on this list, and then evict in reverse order after that. So in this case, tiles A and C will be evicted first. And then if we needed to, we would evict tile B, since it's less likely to be requested than tile B. So we also have our cache coordination protocols, where we have mutual exclusion and mutual inclusion, where with the mutual exclusion, we're enforcing no overlap across caches to basically increase the diversity of tiles stored in the caches and essentially maximize cache space. And then we have mutual inclusion, where the idea is that we want useful redundancy. So we want complete overlap across the caches. So if we evict, say, from the client cache, it will still at least be computed. So we won't take a huge penalty for evicting that particular tile. So with mutual exclusion, say this is the state of all of our caches. So currently this state is not obeying the mutual exclusion protocol. What we do is we run all of our prediction first and then update afterward to clean it up. So here we have our 3 caches: our client side cache, our prediction cache, and our builder cache, which stores the computed tiles inside. And we evaluate from the top down. So with the client cache, there are no caches above it, so it gets to maintain its state. With the prediction cache, we compare with the client cache. So we see that there's overlap in tile A. So tile A gets evicted from this cache. But there's no overlap otherwise, so the tiles stay where they are. With the builder cache, we compare with both previous caches. In this case, we see that there's overlap with the client cache with tile A, but there's also overlap with tile D in the client cache. Then we also compare with the prediction cache. So we see that the only overlap here is with tile C. So then all three of these tiles get evicted from the builder cache. So with mutual inclusion, instead of evicting tiles, we're looking to copy tiles over where there needs to be overlap. So we have the same initial state as before. With mutual inclusion, we compare the client cache and the prediction cache. The client cache stays the way it is. We see that there's overlap in tile A, which is what we want, but we're missing tile D. So this gets copied to the prediction cache. Then we compare with the builder cache. Then we have the builder cache compare with both previous caches. We see there's overlap in tile A. Oh, sorry, that gets copied over. Then we see there's overlap in tile A. And there's also, but it's missing tile D. And there's also overlap in tile C. But we're missing tile E. So D and E get added to the builder cache. So now I've discussed Sculpin's system design and the three major optimizations we developed for it, and I'll move on to evaluation. So the first set of evaluation we did was a two-dimensional data exploration study, where the point of this was a proof of concept evaluation of our prediction framework in the two-dimensional context. We did not evaluate any other optimizations here, and it's just prediction. And we had 18 Earth science researchers exploring satellite sensor data, particularly NASA MODIS, like I showed you earlier, and they were exploring snow cover calculations, like the query I showed you earlier. What was really exciting about this project is that we found, first, that 16 of these 18 users exhibited exploration behavior that closely matched our three-phase analysis model, which is fantastic. And then here's an example of some of the mountain ranges that they explored in the study.
Sorry, quick question. What do you mean that they matched the model exactly?
So the behavior that we saw from each of those users was similar or very similar to what I described with our previous analysis.
No, the part I understood. I was curious about how do you measure the similarity?
That's a great question. So we actually visualized the exploratory pattern. So what we did first is we drew the patterns that we were, so what we did was an analysis of zoom levels. Because in our three-phase analysis model, we assume the user starts at a high zoom level, then zooms into an interesting place, pans around and explore, and then zooms back out. So you're going to see kind of this jagged, mountain-like zoom graph, if you will. And then what we did was we took all of the traces that we collected from the study, and then did the same visualization, and then found that those visualizations, that analysis, matched what we expected from our behavior with the three-phase analysis model. Yes. We also conducted performance experiments where, taking the same interaction logs collected from the study for the zoom out analysis I just mentioned, we also evaluated the average response time and prediction accuracy that Sculpin would have had retroactively. We had a single-threaded CIDB setup where we didn't do anything fancy with CIDB. And we compared with a non-prefetching baseline where every user request triggered a query to CIDB, and then two existing techniques, momentum and hotspot. Momentum basically just predicts that the user's last interaction will be their next interaction. And then the hotspot algorithm is an improvement on momentum, where it takes interaction logs, like the ones we have, calculates the most popular regions in the data set, and then as the user moves close to one of these regions, hotspot will predict that the user will continue to move toward that particular region. Otherwise, hotspot defaults to the behavior of the momentum algorithm.
And do hotspots develop as the users interact with the data?
Yes.
So hotspots are growing as they go.
Yes. And it also depends on how long they analyze. And sometimes, in particular data sets, the number of hotspots is obvious or fixed because they're looking for particular things. It's just very clear what those are. But it also depends on the task. Like in our case, we asked them to look for mountain ranges. And so the hotspots were going to be pretty clear. If you looked at the data ahead of time, you could tell where people might sit. But that may not always be the case.
And for momentum, zooming in and zooming out counts as a different direction than left and right panning.
Yes.
It's all okay.
Yep, zooming in and out are separate from the directions, panning directions. Right. So here are our prediction results. We found that Sculpin provides a 20% improvement in accuracy in general compared to existing techniques, so momentum and hotspot. And we found that a correct prediction resulted in 20 milliseconds of latency and an incorrect prediction in 1 second of latency. And then here we have a chart where on the x-axis, you have the number of tiles that were allowed to be prefetched by each technique. So Sculpin and then the two algorithms that I mentioned, where k represents the number of tiles. So when k equals 3, each technique could prefetch 3 tiles before each user interaction. And then on the y-axis, we have the average response time in milliseconds. And then we have a black dashed line here, and that represents our interactivity threshold of 500 milliseconds that I mentioned earlier. So you see from this chart that Sculpin, the red line, provides significant performance improvements over existing systems. Basically, the lower the line, the better. And you see there's a big gap between Sculpin's line and the others.
I'm curious about the dependence on this and the overall response time of your server system. As those go up and down, do these change? For example, if you have a really slow database system where you're waiting 10 seconds per response.
So if you have a really slow database system, what that translates to is that a prediction miss is much more expensive.
Okay.
So what you'll see are the same trends,
here?
but the scales, but not scale, but you'll see the same visualization, but then the numbers on the y-axis are just going to be bigger.
Okay, so if these were log axes vertically, these curves might stay pretty much the same as you varied that response.
Yeah, so what we found is that there's a strong correlation between prediction accuracy and then basically the responsiveness of the system. And the key thing here is that Sculpin provides consistently better prediction accuracy. So even in the context of a slower database management system, Sculpin will still provide performance benefits over existing techniques.
All right, quick question. You may have mentioned this. Is anybody using hotspot and momentum? I mean, you use them as baseline, but you come out with those as baselines. So who used those algorithms?
So I took those algorithms from existing work. So one system that I mentioned in my diagram graph, I can revisit it at the end of the talk. Okay. But the Atlas system, the immense system, basically existing exploratory browsing systems use the hotspot algorithm or something similar, or the momentum algorithm.
Okay.
So you tell me if one of my takeaways from looking at this, if we had 20 milliseconds if you do it right and a second if you do it wrong, is that you ought to be being more conservative. You ought to be spreading the processing around a little bit, because you can afford to make that 20 milliseconds 80 milliseconds or 300, anything below 500. In other words, you could move that up a lot if you could start to bring the 1 second down. You know what I'm saying?
Yes.
Does that make sense? So there's a sense in which I look at this and I think like spread the processing around a little bit more. I'm not sure that makes sense, but that's kind of my thinking.
When you say spread the processing around, do you mean the prediction processing, or?
I mean, don't be as focused. I mean, because it's like you can afford to. Yeah, you have a total budget, and I feel like you can. It looks to me like if you turn that 20 millisecond with correct prediction into 100 milliseconds, you'd still be okay. And take some of that extra processing and kind of widen your prediction umbrella in some sense. You know what I'm saying? Anyway,
yes.
Go on.
Yes. I'd love to talk about that more after the talk. But
sorry, could you say again what the x-axis was here? I didn't understand.
It's the number of tiles that were prefetched before each user interaction. And every algorithm was allowed to do that prefetching. And K represents the number of tiles. Yes?
So what did the jitter look like?
When you say what did the jitter look like, can you rephrase that a bit?
Like you have average response time, so what's the variation in response time?
So
the jitter.
So users behave differently throughout a session, and then individual users could behave differently. So for the
standard deviation,
has a different, there's more variance than another. Right? The variance is also something that.
What's the distribution of the response time?
Right, you just the averages.
Not the what's the distribution of the response time, not just the average response.
That's a great question. Let me get you those numbers after. So we also performed a 3-dimensional data exploration study where the point was to verify that Sculpin works beyond 2 dimensions, and then also to basically measure the impact of our other optimizations. So in this case, we have 20 earth science researchers, so a little bit more than before, and these are all completely new people to this study. And then we had 3 different sensor data sets that they explored. and in a snow cover data set, which was meant to be the multi-dimensional version of our previous data set for comparison, and then a hurricane and phytoplankton blooms or phytoplankton population tracking data set. And like before, logs from the study were used to conduct performance experiments. So in this case, we have the same chart as before. Well, the same structured chart as before, where the x-axis is the number of tiles prefetched per request, and then the average response time in seconds rather than milliseconds. And then here we have our black dashed line like before, which represents our interactivity threshold. And then we have a green line, which is basically our 2D benchmark. This is the performance we need to get if we want to argue that that Sculpin works the same in a multidimensional context. So as you see here, in the snow cover case, which is our blue line, we basically match our prefetching performance from before. And then for the other two data sets, we meet our interactivity threshold. So I will note here that you might notice on the x-axis we're prefetching more tiles, but this is because in Sculpin's multidimensional interface, because there are multiple visualizations, the user will naturally request more tiles as they do interactions. So we're actually prefetching still an equivalent number of tiles to before, even though there are more tiles.
Sorry, the previous graph that you had was snow cover, right?
It was just snow cover, yes.
Okay. So what's the 20% improvement? How does it look like with hurricane or ocean bloom?
So that's a good question. We focused on just evaluating Sculpin with its previous performance. And it would be a really good idea to also compare with Momentum and Hotspot. But I expect that we would see similar numbers to before because.
Really?
Yes. So even though users are looking for basically different visual artifacts, their general behavior was still the same. So
I'm not concerned about the behavior of the user. I was just thinking about the time to generate the tile that we were talking about before, and how much you need for prediction. That's very much depends on what you said on the problem that you're dealing with.
Yes.
So it will be maybe a naive algorithm will be good enough, and so you don't gain much from what you're doing. Make sense?
Yes, it does make sense.
Anyway.
But so even though it's not plotted here,
okay,
based on my analysis, I would believe that in these contexts, the tasks themselves are similar enough. So even though the visual artifacts are not exactly the same, the general process and the task we ask them to do is quite similar to the snow cover case.
All right, we're out of time. Let's let Leilani finish.
Yeah.
We were applauding
Okay.
Jenny.
All right, so that was only our prediction results. I'm going to move to our end-to-end performance results, where we tested all of the optimizations in Sculpin, and we found that we're able to maintain interactivity, so 490 millisecond average response time or less, for all of our data sets. But we also found that Sculpin provided a 380% improvement in the time required to build tiles offline. So with Sculpin, you can basically produce visualizations almost 4 times faster compared to existing systems, which are the equivalent of pre-computing everything in advance. And then we also found a 374% improvement in the space utilized to store tiles. So with Sculpin, with the same amount of resources, Sculpin can support basically almost 4 times as many queries as existing systems. So in summary, I discussed Sculpin, a data exploration system for multidimensional array data. And in Sculpin, we developed an analysis model to describe how users explore data through behavior-driven optimizations and evaluate Sculpin with 2 studies involving scientists exploring real-world data sets. And we found that Sculpin enables scientists to not only interactively, but also iteratively analyze their multidimensional data. All right, so let me move on quickly to future work, where, again, my goal is to build easy-to-use, data-intensive systems for complex analytics, where I'll talk about my future work in the context of the analysis process, which I break into 4 different steps. Forming and updating a hypothesis about the data, transforming the data, such as by executing a database query, visualizing the data, like I've just shown you with snow cover, and then interpreting those results. And this can happen in a loop, however many times the user needs until they feel satisfied with their analysis. So in my current work, I've supported these 3 areas. With Sculpin, I've improved the performance of transforming and visualizing the data sets that people want to explore. And then I've also worked on another system called String Trace, which I mentioned very briefly at the beginning of the talk, where I developed a visual interface to help people debug and make sense of queries executed on complex temporal data sets. So in my future work, I participate into 3 areas, where first, I aim to generalize the techniques used in Scalable and other exploratory browsing systems. I will improve the efficiency of not only the system, but the human in making sense of the results. And then I'll add support for helping users formulate hypotheses and evaluate hypotheses, particularly in a collaborative context. So first, my first area of research is generalized adaptive exploration systems, where the idea is I want to take the techniques that I've been studying throughout my thesis and other techniques, and I want to support a richer set of interactions. So I think earlier in the talk, someone asked about this. I would love to support other forms of interactions besides just counting and zooming. For example, if we are looking at snow cover, and we know we're interested in mountain ranges, why can't we just tell Sculpin, give me the tiles where the snow cover values are high? Just give me those. Or even better, why can't we just circle a mountain range and then say, find me more stuff like this? And then Sculpin just gives them to me. And then I also want to support, basically broaden the scope of these exploratory browsing systems beyond satellite sensor data to other forms of data sets. So users explore many kinds of data sets with different semantics and structure. And I believe that for exploratory browser systems to have real impact, they need to support this. My second area of future research is automated recommendations for data analysis, where the idea is, if we can predict what the user's doing, we shouldn't just be following them around, assuming we're going to know what they're going to do, and then not tell them. We should just give them what we have and help them perform their analysis faster. Where the idea here is, it's not just the system's performance that matters, it's also the human's performance. Specifically, if we can help the user make smart decisions throughout this iterative data analysis process, we can actually also significantly trim the analysis time down. And one way of doing this, the way I will choose to do this, is through recommendations. So one example is, in the case of snow cover, rather than the user having to ask me what they want, why don't we just look at what they're doing, observe, oh, okay, I think this is what they're looking at, which would translate to mountain ranges, and then just recommend them to the user. Say, hey, I saw you were looking at these. Here's more of them. Maybe you'll want to explore those next. And then here we can short circuit the user's search for the mountain ranges in the first place and allow them to immediately do their next analysis. And in this case, we can extend this to not just predicting visualizations, but predicting analyses, predicting database queries. Say the user has a chain of queries that they've been executing. If we can find a trend in that, we can extrapolate and speculatively execute future queries we think the user might want to explore while they're exploring just the current query. And then when the user's done with their current analysis, we can recommend them and say, hey, we saw you were looking at queries like this. Maybe you'll want to see more queries like that.
So you could like form a hypothesis about the data that they're looking at.
You could form it, you could try to, basically you can see what they're doing and try to write down and essentially summarize what you think they're doing and then extrapolate that.
You could write a paper for them.
That's our job.
That's the long run plan for all of you.
Well, you know, might be easier than hiring grad students, but.
Sorry. But the my recommendation is, I mean, it's interesting. It just keeps me bring me back and back my mind is the fantastic job that Netflix and Amazon do with recommendation. And I'm being sarcastic; they suck. And so, and in a much easier task. Right? So this seems to be a lot more complex of a task than whatever they do.
It's true. So it is challenging. I'm not going to do it tomorrow, but I do hope to do it as a faculty member. And I think what that means is that it's really exciting. There's a lot of work to be done. And what are the steps, right? I think the first step is obviously with a smaller scope, like I mentioned, just trying to make recommendations within a single analysis step, a particular query. Trying to predict the location someone might want to analyze, things similar to what they've been looking at in the past, and then try to build that out.
Do you think this is harder than recommending a movie? Yeah. Really?
Well done.
All right,
what was mentioned before, the first step is
conversation on my, so this is basically my last slide, so
if
we can just hold questions till the very last slide, I appreciate it.
Thank you.
No, I still need to talk about the slides. But, so my last area of future research is in collaborative analysis, where the idea is that when you do science, when you do data analysis, you're not doing it on a mountaintop by yourself where hopefully you have Wi-Fi. You're doing it with, you are analyzing the data with other people. You're showing them your results. You're asking questions of each other. You're formulating these hypotheses together and evaluating them together. And what I find kind of strange is that data analysis tools don't really have a lot of support for this. And so I aim to remedy that. And what's really exciting about this collaborative context, where first I'll start with the multi-user context and then the collaborative context. What's exciting is users might be exploring different data for the same data. They might be exhibiting the same behavior sometimes or different behavior. And they might be utilizing different amounts of resources over time as well. And what I think is really cool is in terms of resource utilization and efficiently managing basically Sculpin across all of these users, there's so many possibilities. You can take advantage of when people are exhibiting the same behavior to maybe do data sharing. You can, when they're doing different behavioral patterns or exploring different regions, you need to be a lot smarter about how you're managing your data, because you're basically doing it for 2 or for 10 or 100 instead of 1. It might be possible that the behavior they exhibit with one data set can be translated to other data sets. So in this centralized context, it'd be really cool to support that. And then in terms of collaboration, I think it's really exciting to look at data sharing and basically optimization techniques in that context. Because, of course, if they're looking at the same exact region, you can probably save a lot of resources by basically sharing between the 2 people. But what if they're analyzing data for the same hypothesis, but in different regions? So even though just because they're collaborating doesn't mean they're doing the exact same thing. So there's all these complexities that need to be taken into account. And in terms of the behavior tracking that I do here, we really need to expand that out to do to support a more complicated and broader, basically behavior model tracker, and then to translate that to resource allocation across many different people using the same system, I think is very cool. So that is the end of my talk.
I have a very simple question. I'm not sure if so. There are many scientists here, and we certainly appreciate all the tools that you're building, among others, for us to better manipulate the data and understand what's going on. However, my question is, do you see any of these cool things being pushed to the masses more broadly? Right? I mean, despite of because this is useful for a very narrow group of people, right? So, the best people out there, right? However, my question thus is, what are the scenarios where you see these kind of techniques being pushed to the world more broadly beyond science and big data analysis in that context?
That's a great question. So what I love most about my research is that it's not just about performance. It's not just about making fast systems. It's also about considering what the user's doing and trying to help them. And so part of my future work I see as not just making the performance of analyzed systems faster and better, but also in building systems that will, that will adapt to the experience and expertise of their users. That's what I want to do.
So
and I
can
think,
you give me an example scenario or application?
So an example scenario would be having a system that could be used by people with multiple different levels of expertise. So for example, if we could build a system that would adapt its interface and adapt the technology that's presented to the user based on level of expertise. Maybe a beginner would get a different kind of interface from an expert. And in that sense, you could see it as part of a training program where the system might manipulate itself based on the user's experience. So as they become more experienced, maybe they see more complex features in the system. And I think that's one way of helping people who don't have a heavy STEM background to be able to use tools like this. I think having systems that adapt to the user is really important.
Then you want to take into account whether the user cares about what they're looking at, perhaps. I mean, if you're just going to show someone who's no expertise in thing a slower, dumber version of what you're going to show the scientist, I'm not sure they're going to be very excited to click on the interface.
I wouldn't think of it as a dumber version. I would think of it as maybe because of their expertise level, they don't necessarily have super intense, complex demands. You know, like they are probably not doing an intense high-dimensional data analysis. But maybe what they need is an easy way to visualize the data in the first place.
But maybe the people are different. They're not scientists, not because they're just dumber. Maybe they just don't care about snow cover. Maybe what they care about is traffic, like to bring up the thing. So you might.
So if you're analyzing traffic, I think this system would still work quite well for you. It's a similar context. I would say you're right. I would think it as more as the users will care about different things. It's not necessarily that they're dumber.
Right.
And I'm saying the system should adapt to what it believes the user is going to care about. But also, I think their ability matters, right? You shouldn't. If you're familiar with the game Kerbal Space Program, that's like an intense, complicated game, and it would probably benefit from showing user fewer things at once until they get up to speed, and then allow you to twist more knobs as necessary. I see a lot of hands up. I'm having trouble remembering who.
I think the prediction not only related to user behavior, but also heavily related to the domain of the application. So therefore, if you want to generalize your method,
yes,
you need to take into consideration of the application domain knowledge.
Yes, this is absolutely true. What I'd love to do is build a system that can basically learn context without. So what I do not want are systems that are built basically by hand for specific domains. I would love it if I want to research possibilities for learning that context from the data and maybe from past user interactions. So for example, if we could take log data from other tools that are used in that domain and then learn from that how to structure other tools, that would be fantastic. Yes.
Okay. I'll try to kind of address Alex and Robbie's question first. Perfect scenario for use of the system would be different working groups to manage infrastructure. They're going to be querying.
We don't care about your answer, man.
No.
That's true. That leaves me. We can talk to you. We can talk to you tomorrow.
That leads me to my question. That leads me to my question. Since slide number 24, 25, when we started using the tiles and all that, and while the top we use multi-bin, for bathroom and so on, but you also use the term database. So yes. What about data warehouse? That stores different levels of granularity or different dimensions, and since most of the processing is done offline, would it make sense to rely on the backend of a warehouse-ish type of solution instead of a database?
That's a great question. So I think depending on the context, it certainly could make sense to use data warehouse. I think, at least in the context of scientists, I don't know how commonly used data warehouses are. I think that might be more enterprise level. But I think as data continues to scale up, data warehouses make a lot of sense. And I'd also like to reiterate, these techniques are not dependent necessarily on the type of data processing backend you have.
Yeah, that's what I meant. So would having a data warehouse enable you to switch between the contexts quicker, because they would provide materialized answers to multiple queries across multiple contexts. So would that help the visualization part?
So do you mean like data queues or OLAP context? I think it would be very hard to support complex analysis with that. With basic analysis, you could, and there are already systems that provide efficient data cube exploration. I think this is a different context. You could certainly use it in the same context, but I think there's limitations to what data cubes can provide for you, and a lot of that is flexibility and being able to do ad hoc queries that are more complex in aggregation. So, sorry, I think.
I think what would be helpful for me is to talk a little bit about the limitations of the techniques that we're using right now, and in talking about some of the future work, what kind of techniques would be useful that the current techniques don't support, right? So, I think you're getting a lot of questions about how do you generalize the different domains? It's like, okay, well, you need domain knowledge, but you don't want to build domain knowledge in, but now you need some kind of very general knowledge, but very smart system that could somehow figure out people's behavior patterns, right? So the user model in the current system is somehow domain agnostic to a certain extent, at least within that style of interactions, but it's also rather simplistic as a user model, right? In terms of what users can do. So how, could you just speak a little bit to the limitations of the current techniques? Having already said where you want to go with the work, what kind of techniques would be needed to get us there beyond the limitations that the current techniques have? Could you speak a little bit about that?
Yes. So I think one limitation of the work is it's not clear how it translates to data sets or contexts that look very different from, say, satellite sensor data. For example, when you're analyzing, say, DNA or gene data, that kind of biological data, they have, so part of it is the kinds of visualizations that people use in these different domains. Right now, we're making the assumption that sort of this one interface is going to work well for a variety of contexts, and it does. But when you start going beyond these kinds of visualizations, or this kind of interface, you start to run into some bumps. For example, with when you're analyzing, like genomes, you use completely different interfaces and different visualization techniques, which means different interactions, and would probably the structure of Scalable would probably have to change at least a little bit to be able to support that. So I think what would be really useful is to, so I hesitate to say this because I know there's already been work on taxonomies, but to really characterize the different interactions for different, basically what we need is to sort of have a taxonomy of data sets actually, or contexts, see the tools that are used in those contexts. And I think another question that needs to be answered is, are those the right tools? Are those tools truly unique? Are there maybe parts of it that are reusable across domains? And then for the things that overlap, we can do those immediately. For the things that don't overlap, we have to decide, okay, if we add these techniques to the system, what value do they bring? Does it make sense to, for example, add genome sequencing visualization support or exploration or search support to this interface? I think in terms of the context of broadening the scope of something like Sculpin, there are a lot of challenges there. As far as bridging the gap to domains that seem far away from where Sculpin is now. But that being said, what I think is really interesting is adding interactions that are common across many interfaces. For example, pretty much everybody wants to do a data set search. Doesn't matter what data set you have, you probably want to look for something. So doing that kind of lookup absolutely makes sense. And then to an extent, being able to scroll through the data that you're looking at is also a pretty common, I think a pretty common interaction, though even though it's simple, still bridges these gaps.
So I guess maybe without taking too much time, just what kind of literatures do you think would be useful for you to build this research on top of, right? So like, okay, so we want to move to another field. We know we have to add these techniques, but in general, if we're going to get these techniques to scale and to continue to get these efficiency gains, what literature would you be drawing on? What fields of study can you borrow from to inform these models that you need?
I think like psychology and HCI could be very useful in terms of behavioral modeling. So there's existing work right now. Analyzing interaction logs is pretty hot right now, I think, in visualization. And it would be great to pair with people there to do more sophisticated log analysis. So like you said, this is kind of simple, but we're just starting now to do more exciting things with log data, I think. And there's a lot of room for growth. I also think that for the domains that we want to support, it's important to make connections there and partnerships, because to really understand how to best generalize the systems or apply them in other domains, it makes more sense to understand how that domain works. So, for example, if I wanted to support astronomy data, I should probably talk to astronomers. And if I am serious about supporting medical data, I think it's important to partner with people who already work with, say, doctors or scientists working with medical data. And then I also think another area that's going to continue to be important is database research, because yes, I focus on user behavior and take advantage of that information to do performance optimization, but you're only as fast as your database or data warehouse. So I think it'll continue that'll continue to be important.
All right, so let's think this big.
Lots of questions.
I can't believe that first one.
Yeah. Okay, refresh me, that's the one that you hope is going to be, but she's like 2 points below the, I don't know. Past paper. But I'll certainly make it.
Yeah, there's more. What do you have?
Was it?
They're not, that wasn't your difference. But you, I think you addressed everything. That everybody asked tomorrow.
Yes, I do.
Actually, it is.
Thank you.
Time is really
Two baskets first.